Now, before we talk about two-point perspective, we have to talk about a couple other mathematical things. In particular, the humble square and the crop factor and what a crop factor is. Let's start off with our humble square. So, if you recall from grade school, there are a couple things that distinguish a square. Number one is that each side is equal length. So from here to here, we'll say that is, let's call it something that's easily divisible, like uh, 8, 8 units, right? So we have sides that are 8, 8, 8, and 8. Another thing that distinguishes a square is that all four angles are going to be exactly 90 degrees. So, how big are these? 90 degrees. 90 degrees. And just to differentiate this, let's compare it to a rectangle, because a rectangle is still got a lot of good stuff going on. It's just going to be slightly different. So this one we could say this is, I don't know, 6 and 10. But the angles are still 90 degrees, right? Now there are a couple things that are really nice that we can do with this. Number one is cutting diagonals. If you cut diagonals on a square, you get something really amazing. First off, when I do this, we have this new point directly in the center. And do you know something about this point? It is exactly the mathematical center, and it's going to give you everything you need to know for the exact middle of this. So if I have a line going like that, excuse me, I can use that dot to figure out the exact center line that I need. So by using these diagonals, we get a mathematical precise thing. Now what's amazing is we also get a bunch of new things we can measure. So if this was 8 inches across, now we can say that this is 4, this is 4, this is 4, and this is 4. All those are 4 inches long. The other thing that's cool is we can get an exact division here. What's half of 90? 45 degrees. And all those inner angles are going to be 45 degrees too. Now you can also keep using this square to get further and further divisions. So for instance, what if I went from here to here? And I went from here to here. I also went from here to there. And from here to here. Now I've got a square inside of here that is exactly 45 degrees rotated. This square is 45 degrees rotated. And also, all of these inner lengths are going to be, I don't know the lengths, but you can figure it out. There's a mathematical formula for it. And again, we're going to constantly get 90-degree angles this way, 45-degree angles like here. And another thing that's really, really important is imagine we had a line that was just over here. Well, this line, if it's at a 45-degree angle, like this one, my hand-drawn one was pretty close, we can guarantee that it's parallel to this line. Let's get a new color. So these lines are all parallel, just like these lines are all parallel. And also, we can figure out a lot of perpendicular lines to these. So for instance, this line is parallel to this. This line is perpendicular to this one. And you can just constantly know that, number one, you're cutting lengths in half. You're cutting angles into 45-degree angles. And you're generating new perfect squares inside of this. Why does that matter? Well, eventually we're going to get over here in perspective. Just a freehand draw perspective square. We'll learn how to set this grid up, but for now we have this, and assume that I placed this on the ground correctly. I could now, if this was a perfect mathematical square, cut my diagonals, and if I had a vanishing point over here, I could use that to further generate accurate perspective. So notice that now if I draw a line through this exact center, just like when we drew a line through this exact center, we're getting a square in perspective. And what's really cool about this is you can see how perspective works. We're getting a lot more distortion way up here in this square. And as we recede, we get less and less. The other thing that's cool is there was probably an extra, just to show another thing. So if I did have this grid, and imagine there was a vanishing point out here, these lines going through here and through here would also give us an angle that would, in theory, again, I didn't draw an actual grid, so it's not perfect, but in theory it would be exactly parallel to this line here. Now what about a rectangle? Well, there's a couple things that we can still do with a rectangle. If we cut these, we might not get an exact mathematical basis, but we do still get midpoints. And we still get right angles. The one thing to know that you do not get is you don't get 45-degree angles. So this is like 30 and 60. And if you had a bigger setup, you could prepare for that. But you could do things like make a square. Excuse me. You could do things like make a square, duplicate that square, and now you would know a little bit more about the math here. So on this square, we know that this is, I don't know, 5 units. 5 by 5 by 5 by 5, 5, 5, 5, 5. In other words, this is actually 10. So if I cut it in half, I cut this in half, we can still get some pretty cool math. Or for instance, this we would know it's exactly 5 by 2.5. Okay. Let's delete all these later. Now another thing we have to consider before we start getting into these harder problems is the crop factor. And I think the best way to consider this is imagine you have a camera. So here's your camera. And a camera has a couple of components that we care about. Number one, we have an image sensor back here, which is just a plane of computer sensors or diodes, very similar to your eyeball. And over here we have a lens. Now this lens is going to have various numbers, but let's start by examining this camera, this image sensor. This image sensor is going to have an exact size that it uses to generate images. And I believe the way that they calculate it is, I could be wrong here, but I think it is that the diagonal is 35 millimeters. So when you see 35 millimeter cameras, that's what it's referring to. It's referring to the size of the image. Now over here we have our lens, and you probably have seen numbers like 16 or 8 millimeters or 300 millimeters on a lens, or it could be even be a range like 24 to 70. What does all that mean? Well, your lens is just this thing that's either that big or this big, or maybe it's really tiny like over here. And the way light works is that light streams in from your lens. Let's start with this basic one here. So imagine we're working with this lens right here. The light travels into the lens like this, and all of the information, just like that pane of glass cutting our initial outlay, is going to cross at this thing called the nodal point. So we have image sensor, nodal point, and what these numbers on the lens represent is actually very simple. It is the distance that it had to travel. So, for instance, this lens here, just to freehand it, this lens is probably 24 millimeters. Because look, if this is 35, and that's 25. If I had a lens right here, in other words, about half of this distance, this would probably be a 16 millimeter length. Now what happens when you have a really, really long telephoto lens that can see really, really far? That's going to be a 300 millimeter, perhaps. You can even make it bigger. Now what's cool is notice how as I create that nodal point to go through this lens, this image is getting smaller and smaller. So what ends up happening is we get a very, very narrow depth of field for this long lens, whereas for something like this 16mm lens, look at this. It's a huge angle. There's our wide angle. I'll choose a different color so it makes more sense. Look at how big this angle is. That's a lot of stuff you're seeing. Now, how does this matter for two-point perspective? Well, let's go back to that idea of you standing here. We're going to do another top view. So here's you, Cyclops the viewer. Here's your eye, optic blaster. Here's your feet. Here's your shoulders. In other words, this is where you're viewing stuff from. And you shoot out this ray. And this ray has something that could be considered parallel to it. It also has stuff that could be considered perpendicular to it, like that line. Pardon me. Let me start over. You could have rays that are parallel to this. You could have rays that are exactly perpendicular to this. And you can have lines that are exactly at a 45-degree angle from this. So generally speaking, let's say we had lines extending out from here that were at that direct 45-degree angles. We now know that this angle is 90 degrees. So that angle is 90 degrees. In the same way that this one is. Or this. And this, to get to this one, to get from this square to this one, what do? You rotate it 45 degrees. So oftentimes when we're viewing things, though, we don't actually see what's over here on this 90-degree angle. Sometimes we might be seeing something that's closer to that 300mm lens. Or perhaps we're using a lens to bend the light. And that's how you can get something where you have like 8mm. So just know that as you get a crop, you're going to get various picture types. When you start off, you might have a scene that's like very, very, very distorted, right? So up here, you have something where perhaps there's a person on a bicycle and they're practically coming right at you. And this is on something where we can actually see these two-point perspectives, these secondary vanishing points. But usually, what you're going to have is something that's kind of a crop of that, like this. And you can imagine this by actually creating a viewfinder. Just take a piece of cardboard and cut it out, and you can move it around. And wherever you go, you can get some different idea of what you're cropping. And what you see with that crop is represented by that millimeter distance. Alright, so based on that, let's assume that we are going to be able to view our secondary vanishing points. Let's start by adding our horizon. And we're also going to add add our principal vanishing point right here. In other words, we're going to use this for things that are parallel to our line of sight, aka they converge over there, and lines that are perpendicular to our line of sight, so perhaps things that are on the ground and receding infinitely. But for now, we're also going to add our secondary vanishing point. So over here on the edge, I'm just going to assume that our secondary vanishing points are visible to us. I'm going to label this 2VP, which is shorthand for secondary vanishing points. We also have our horizon, and our principal vanishing point. Now let's draw just a line here that is directly in the center and something that we could see going towards that principal vanishing point. So again, it's going to be one square on each side coming directly down from this secondary vanishing point, right? And I'm making sure that it goes about there. And then I'm going to have this eventually converge at our secondary vanishing point because it's traveling off into the distance. We can even label the units here because we want to make sure we're caring about that. So let's call that 4 inches, 4 inches, and this total would be 8 inches. So when we have these secondary vanishing points, remember that our viewer is up here. He's looking out. This is a parallel line. Did anything going this way? This is a perpendicular line. And our secondary vanishing points are going to represent what's going off at a 45-degree angle from that. In other words, what happens when we have a 45-degree angle and we cut the diagonals of a square? Remember that we found the exact midpoint. And we can keep doing this constantly. So we can say this is 8, this is 4. And we can actually do this forever and say this is 2, and this is 1. Let's use this math of 45 degrees to our advantage. So going from this point here to our secondary vanishing point, I'll actually start back here. Now, just based on this one line, what do we know? First off, we also know that this is a 90-degree angle, that these are 45-degree angles, and that if this is exactly 45 degrees, then if this whole side is 8, actually, get rid of these 4s. So if this front plane is 8, then we now know that this point from here to here is also 8. And it doesn't look that way because perspective is so awesome in how much it distorts things, right? This line in perspective is the same as this line receding backwards. Now we could actually just go off of this line from here, and this is going to give us enough mathematical precision that we actually don't need to draw the other line to say that if this is parallel to this, these two lines are parallel, and that's all we need to say that this is an exact mathematical square. But just for the sake of argument, I'm still going to do it because it's kind of handy. Oh, wait, no wonder. I didn't see I had a computer glitch when I drew that. I thought it looked a little cramped. There we go. So again, one last time. 90 degrees. 45 degrees. And this is also going to be 8 inches. And also, if I now use this line, this is a perfect square in perspective. Based on the math of how this square cuts out, it's always going to work. And what's great about this is, guess what? Based on how perspective works, this line is actually the same length as this one. Eight inches. Which means that we can actually do this whole process over. So now I can go from this spot so now I can basically assume that I'm doing this whole thing over. Go from there to there, and from here to here. And from here, I can cut this back edge. And I actually, again, don't have to use that line. I'm starting to get limitations to my results based off of two things. Number one, the size of my display. And also the size of my document. You can see this is pixelating. We can use this infinitely to get these perfect squares. Now what if I had this line over here instead? Well, this line is still going to function correctly in perspective. So I could have it go backwards as long as these two lines are parallel to each other, which they are. And any lines that converge on the principal vanishing point are going to be perpendicular to this line and parallel to each other. Then that means this is going to be a 90-degree angle. And so is this. And this is where perspective is so cool. Does this look like the same angle? Not at all, but this is actually how it distorts. This and this are both 90 degrees. Now what's really cool is I can continue to also cut my diagonals from here. So if I go from here to my secondary vanishing point, this is going to be my back edge. And wouldn't you look at that, it lines up perfectly with the other one. And you really can't keep abusing this math forever. What if I wanted to find a line that went directly down the center of it? Like, what if I did this, these two lines going to the principal vanishing point first, and now I needed to assume it was a road and put a line going down the center of that road. Well, I can just grab the principal vanishing point, and if I can cut that diagonal, I can go through that exact center, and now I have something directly in the middle. Pretty neat stuff. Now again, I can also make something that is a rectangle. It's a little less mathematically rigorous. And it's just going to have some differentiations. So let's say I don't cut this diagonal. Let's say I just throw something there. Well, if I cut this diagonal, note that in no way is this going towards this secondary vanishing point. In other words, these angles are definitely not 45 degrees. But we've still found something useful. I still have the exact center of this, right? So I can still grab this and get something that goes through the exact center. And now I could actually even cut this. Now again, why did I show you crop factor? Because the fact is, the majority of times when we're going around in the world, we actually don't see these secondary vanishing points. We're going to have something that feels a lot more cropped. Something like, oh, I don't know. There. And in fact, if you see something that's really zoomed in, it might be more like this. If you zoomed in even more, it could even be something like this. Now, if you do all the math that generated these squares, eventually, I'm just going to freehand draw this, but eventually you're going to start having something. So notice how narrow these squares are back here. So when you have that crop factor, you're going to start seeing that back here. Like, these are going to be like very narrow squares until eventually they just look like lines and dots. And just due to the size, you're not going to really draw them out individually. So it's always important to just have that as a consideration. Alright, next up, let's talk about scale and how you might actually use these things to start setting up a scene.